Hello everyone, welcome back to Bytes of CAC. So in this lecture, I'm trying to give you a bird's eye view of the entire networking subject as a whole. With respect to the layers in networking, when I was a student, I used to be so confused about so many layers and the different protocols in each of those layers. And just making a wild guess that some of you might be needing some help regarding that, I have decided to put up this video. So in this video, we will be talking about the major functions of the different layers in the TCP, IP and the OSI models and the different protocols that are used in each layer, the important ones of course. Now this video is going to be a long one, so I do not wish to make it longer, so I will not be discussing the protocols in depth. I will be dealing those protocols in different lectures in future videos, but for now I will just be giving an overview of those protocols. So let's get started. And before starting, see, in your textbooks you deal the subject like the subject is dealt from the physical layer, that is the lowest layer, to the application layer, which is the highest layer in both the models. But when you interact with the system as a user, you actually interact with the application. And as you interact with the application, your request goes to that particular machine, the particular computer, and you get the reply from that computer. So if I have to view it from an user's point of view, it is better to start with the application layer itself. Like for example, in this video, you will be seeing that I'm trying to access the RSA protocol question page from the Bytes of CAC website. So I just copy and paste the URL, press the enter button. And when I press the enter button, the task of the networking kicks in to the time when I get to see the questions, the actual questions in my web browser as I'm seeing it now. So if I take this example, so first is I go to my Chrome application, the web like the web browser application, the Chrome here, and I just put in the uniform resource locator or the URL. But see, when we contact, like when we are trying to interact in this networking system, one computer contacts another computer for the file or the web file that is hosted in the Bytes of CAC server. Now I haven't given the IP address or the address of that computer where the files are hosted. So naturally, the first task is to retrieve that address of the computer or the server where the files are hosted. So in order to do that, we use the domain name system. Now the domain name system, the main task of the domain name system of the application layer is to map the URL to the IP. It somehow finds out where this URL or this resource is located, like which computer hosts this resource. After it is done, it appends this IP address, or it inputs the IP address and to the message, and it hands it over to the next layer or the presentation layer. Now, if you are using an OSI model, application this after fetching the IP, the message will be forwarded to the presentation layer. But if you are using the TCP IP system, it is still in the application layer. Like presentation layer does not exist separately, but of course these functions do exist. Now in the presentation layer, the main thing it does is to decide the data format for the data exchange. Now each system in the network, or each of the computer systems that exist, they are free to choose their own data format. But the problem is, when two computers interact, it might be that the data format used by this computer is not understood by the other computer. So there must be some standard that makes the communication process or the deciphering process easy. So we have such data formats like HTML, XML, JSON, and so on. And which of the data format will be used is decided by the presentation layer. And next, another important task that it has to do is, if we are to encrypt the message, if you are sending the message that needs some encryption, that is also done in the presentation layer. When the presentation layer is done with its job, it adds these information to the header part of the message, and it forwards the message to the next layer or the session layer if it is a if it is an OSI model. If you are using TCP model, TCP IP model, it's still in the application layer. So this session, presentation, both belong to the OSI model, not the TCP model. Now, the main functions or main tasks of the session layer are session management and synchronization, like who's going to, in which order the messages will be exchanged, who's going to go first, who's going to, how the connections are being made. Everything is decided by the session layer, and this is important. The synchronization part is very important if you are dealing with a common data, maybe a common data that will be updated or used by both the client and the server, that is both the computers. So in that case, how the data is to be accessed, that needs to be decided first. Otherwise there will be some problem, there will be some data like the database might be in an inconsistent state. And next is checkpointing. Information is also maintained by the session layer. Now, if you have learned about checkpointing in your DBMS, you already know that checkpointing is actually a log record of how far the system has proceeded. So in this case, how far the conversation has proceeded. This is very important because sometimes there's a link failure, or it just the two computers get disconnected with each other. Now, if this checkpointing information is maintained, when the link again the connection like the two computers get connected again, they can just go through that checkpointing information and they can start the conversation from that part. Otherwise they have to start it over again. So these three layers in OSI model, or this application layer itself in the TCP IP model, deals with process to process delivery. So in this case, the client application, the web browser application of my computer is trying to contact the server application of another computer at some IP. Now IP address, like it looks like, I think many of you have gone through this 192 point say 17.57.6 and so on. If it is a IP version 4 address, IP version 6 is a little longer, so I'm not using that. So now after doing everything, like the message is delivered to the next layer in both the TCP IP and the OSI model, that is the transport layer, which also deals with the process to process delivery. Now, when it receives a message, it first checks against its own frame format size. Now, transport layer has a fixed frame format size, and if the message size is longer than that, it will segment the message and number each segments accordingly. Like this is divided into 5 segments, as I can see. And then now when you are dealing with like when you are using your computer, like in my computer I have so many applications running at the same time. The game application, then maybe MS Word application, then my browser application. Now when a reply comes from the server, it first will reach the transport layer before reaching any of the 3 previous layers. So now the transport layer needs to know that where or whom um, to forward this packet. So for that reason, it uses something known as a port number. So port number actually is used to mark a process. Now port number is a 16-bit number that starts from 0 to 65,535. Now the first thing is that it will add a port number to your or to my web client, and that port number will be anything from 49,152 to 65,535. Now if you are thinking that what about the port numbers from 0 to 49,500 49,151, so those are actually reserved port numbers for special purpose. Now one example if I give you, now the client or the port number of my machine is sorted, but it will also need to provide the port number of my server machine. Now it doesn't know which port number the server or which port number is going to handle the web file. So to deal with that problem, there are some reserved port number or universally agreed upon port number from 0 to 1023 that is used for your destination machine or when we are trying to contact a server. For example, this is an HTTPS application, and there are three kind of protocols, communication protocols used by the transport layer: the UDP, TCP, and SCTP. If it is using TCP kind of connection with the server, the port number of my destination machine will be 443. So it is a universally accepted port number. If your machine also tries to connect to the server that hosts this bytes of CAC, so this is actually an HTTPS kind of connection. This will also map that port number to 443, the port number of the destination host. So the port number along with the IP address is together known as a socket address, which will be used by the transport layer for communication. Now this UDP kind of communication is a connection less communication. It provides no flow control and very minimum error control policies, and this is used when your message size is really low and not that important. Now TCP is a better protocol compared to this because this is connection oriented. It provides its own flow control, error control mechanisms, but TCP has certain overhead. So if your message is not that important, you probably won't be using TCP. And next, SCTP came after UDP and TCP. That is because TCP gave rise to one kind of network attack, which is known as the denial of service attack. So in order to address that denial of service attack, SCTP came into being. So now transport layer also deals with congestion control. Now congestion happens in a network when the traffic of your networking channel is more than it can handle. So there are several ways of dealing with the congestion control. This open loop is about preventive policies, and it has got policies like retransmission, acknowledgement, discard, and admission. So retransmission, acknowledgements, these are used very judiciously. Especially TCP has a very good retransmission policy that makes sure that the congestion doesn't happen. And discard and admission is like, say when the network traffic is getting the traffic is getting heavier, the nodes starts discarding packets or start discarding the messages you send to them. And same with the admission control. When the traffic is slowly getting the traffic is quite high, then they deny connection to other machines. So if another machine is trying to contact that machine, it denies a connection establishment. Then we have closed loop congestion control, that is, after a congestion has taken place, these are the policies that kick in. These are like back pressure, choke packets, implicit and explicit signaling, where back pressure deals with when like it starts not accepting those packets, and finally the sender gets to know that all the packets it's sending is actually getting discarded. Then choke packet is like a signal, it's like a control packet which is sent from the destination to the source, which says that this network is too congested, so please don't send us any more packets. Then you have implicit signaling, where in implicit signaling the sender does not get any acknowledgement that the destination machine has actually received the packets, so it assumes that there might be a problem or a congestion in the network. And in explicit signaling, well, if it is a two-way communication, like the sender is sending a message and the receiver is providing a reply, so in that reply message there's a special bit that indicates that there is a congestion in the network, so please slow down. And then we have traffic shaping. Now traffic shaping is about maintaining a constant rate of traffic in the channel, so that is done using leaky bucket and token bucket mechanisms. Now, after all this is done, deciding which protocol it is going to use and mapping the port address of the sender and the receiver, it now hands over the message to the network layer. Now, network layer deals with host to host delivery, that is machine to machine delivery. Till now we were talking about process to process delivery. From now on it will be like machine to machine delivery. Now, a lot happens in your network layer. So, network layer, actually, before we delve into what a network layer does, we need to be clear about two things. One is the autonomous system. Now, if you look into your internet or the internetwork, it is actually a number of networks or sub networks, as we call it, that are connected with each other so that the entire globe is connected. So, when we are trying to send a package from one machine to another machine, say I am sitting in Delhi and I was trying to access a server of bytes of CAC, which might be hosted, say, in San Francisco. So, this has to be geographically transported from Delhi to San Francisco. So, the route must be known, how to get to, how to reach to that. But if you have to know the route, or if you have to know where each destination machine is present, how to get to each destination machine, and that is going to be a lot of data, and this is very difficult to actually maintain so much information. So what we have done is we have chosen a few in sub networks together, and we have marked them as an autonomous system. Say we are taking these three networks, this blue, green and black, that is one autonomous system. Next we are taking these network together, say this orange and green together, and we are calling it, this is some autonomous system 2, and so on. Now this will help us. In this way, the entire internet network is divided into domains or autonomous systems, and it will be difficult to manage information regarding them. So that is point number 1. Next, we have another thing, that is a router. Now, a router are those network device. It is also a computer which joins two or more subnetworks, or LAN or WAN, whichever you would like to call it, or whichever it is actually. So now when we are forwarding one package, now it is highly unlikely that the package I am going to send belongs to the same network as I am in. So now we need to, now the package is actually forwarded to a router. that is one that is connected to more than two subnetworks. So it moves from one router to the other router, and in this way it moves to the actual destination. For example, say I am sitting in Delhi, as I said, and my my router is directly connected to another router that is in Mumbai, and also other routers, one in Bangalore, and so on. Now, if, for example, I am trying to send some traffic or send some message to to a computer that is present in San Francisco, it knows that if it sends to the router in Mumbai, so Mumbai sends all the packages to say Europe and USA. So if it sends over this package to Mumbai, Mumbai will find a way out to send that package to the San Francisco system. So routers are very important in this network layer. So we need to keep information regarding the route. So that route information is obtained or maintained using three protocols. This is routing information protocol, OSPF, and BGP. Now these two protocols maintain information regarding the same domain, the domain where it is in, and BGP, or the border gateway protocol, it maintains information about the inter autonomous systems or the inter domain information. Now, in the network layer, as it receives the message from the transport layer, it might need to break down the transport layer segment again. Now, each subnetwork in this system, it has a maximum transfer unit or the frame size, and if the segment size is greater than this maximum transfer unit, that segment needs to be broken. But now, whenever the package is forwarded to one router, every time, because see, every network has its own MTU. This MTU is not a universal thing, so every network will have its own MTU. So now if router A, say it forwards to router B, router B's MTU is something, then again say router B is sending this package to router D. Router D will again compare its MTU with the segment size it receives from B. So at every router, this process will be carried out. And also, in every router, will check its internal table where it maintains the route information, and it will forward to the appropriate router. So it moves from machine to machine in this system. Now, another problem that happens is when it moves through a network. So till now we were using the IP address or the logical address, but when you are actually transferring a package from one host to another, you will be needing the physical address. Now, what is the physical address? Now, this physical address is actually the one which is imprinted in the network interface card of your computer. Now, you might argue that why are we using this logical address? We can use the physical address only. We would be using just one address in that case. Now, the problem with using physical address, the main problems are, number one, see, your network interface card might get destroyed, or there might be some problem to your network interface card and you might have to change that. So if you change that, your physical address is also going to change. And the second problem is the address space or the number of bits actually used to do the physical addressing is much less, and there are so many devices across the network, and we actually need to have a universally like universally unique address in order to identify a machine, and that is not possible using the physical address, because physical address is unique. Each physical address is unique to its own network, but not unique to the entire inter-network service. So now we will be needing another protocol to do this logical to physical address mapping to actually move those packets along the network. So that is done using the address resolution protocol. So address resolution protocol is another protocol that works in the network layer. Now, the main communication protocol used in the network layers is the Internet Protocol. There are two versions of it, IP version 4 and IP version 6. This is the newer and, of course, the better version. Now, the main problem with Internet Protocol is Internet Protocol does not provide any error correction or detection mechanism. It assumes that the other layers will be taking care of it, so it will not be using that. But oh, one thing I think I have forgotten to mention about in the transport layer is transport layer also has an error control information which is known as checksum. I will be dealing with checksum in, of course, a few lines when the data link layer comes. So checksum actually helps you understand that if the package that has arrived is error free or not. But well, network layer does not provide anything of that sort. So there is another protocol defined which is known as ICMP, which does some querying and error reporting services. Like for example, I don't know, I think some of you have also used ping in you have written like ping in your command prompt, have added some IP address and have pressed enter to see that if your computer is connected to that computer. So that is actually a part of the ICMP protocol service. So now another thing is, as I said, there are so many subnetworks that are actually connected to form the internetwork. So each subnetwork is free to use its own version of IP. So now this is completely a heterogeneous system where some subnetworks will be using IP version 4, some will be using IP version 6. But the problem is the header or the information, the metadata information used by IP version 4 is very different from IP version 6, because even the IP address itself is going to differ, because IP version 4 uses a 32-bit address, whereas IP version 6 uses a 128-bit address. So you see there are so many differences in both the versions. Now it might be that, say you are using IP version 4 and you might have to go through subnetworks which uses IP version 6. So what will happen in that case? So to deal with that problem, we have some transition strategies. In dual stack, a particular subnetwork supports both IP version 4 and IP version 6. Tunneling is used when both the sender and receiver are using the same version of IP, but somehow it has to go through subnetworks, the intermediate subnetworks, which are using a different version from theirs. So tunneling is used in that case. And finally comes the header strategies. This is used when the IP version of sender and receiver are not same. So after all this is done, the package is now forwarded to the data link layer. Now, data link layer is logically divided into two parts. One is the media access control layer or the MAC layer, and another is the data link control layer or DLC. Now, media access control layer is actually concerned about accessing the transport media. And after you have got access to the transport, that is the wired or the wireless media, then the data link control layer protocols, they start kicking in. So the main functions of the data link control layer is flow and error control mechanism. Now in media access control, uh, we have different ways of accessing the actual physical medium. So one is the random access, which is very simple, where we will be using Aloha, a protocol. There is pure Aloha and slotted Aloha. Pure Aloha is when you have a message to send, you just send the message. And slotted Aloha actually slots the uh, entire time. It just slots the entire time into intervals, and you can send a message only at the start of an interval or start of a time slot. Now, why it was done was, see, pure Aloha works fine if the channel is used, it's a dedicated channel for two computers to communicate. But seldom we have that kind of channel. Most of the channels that we use are shared channels. Now, if a number of stations are trying to send data simultaneously, there's a collision and none of the data actually reach their destination. So, in order to prevent that, not actually prevent, just as a measure to lessen those kind of collisions, slotted Aloha came in. Then we have CSMA, or carrier sense multiple access, where there are two kinds of protocol of collision avoidance and collision detection. Now CSMA, before sending the message, it tries to sense that if another station is also sending, but apparently this also has its own failure points. So now came the controlled access. Now in controlled access, a station who is trying to send needs to announce beforehand that okay, I'm trying to send. Or there must be some station, like in reservation it actually says that okay, at so and so time I will be sending a message. So every station knows that at this point of time, like station X is going to send a message, so they usually refrain from sending their own message. Next, we have a polling where a primary station or a big boss kind of a station is elected, and that big boss decide who sends when. And finally, we have a token passing process where one token actually moves around the network, and whenever a station or a device needs to send something, that device grabs this token, sends the message, and after it is done, it releases the token. So if a station manages to grab the token, it knows that none of the stations are actually sending. And if it is not able to grab the token, well, it knows some other station is sending, and of course, it cannot send without grabbing the token. And finally, we have channelization strategies where the channel is divided according to frequency, time, or code. This is the frequency division multiple access, time division, and code division multiple access. Now, after it has gained access to the medium, next comes the data link control layer protocols. So, first is the flow control. Now, there are two protocols in flow control, that is the simplest protocol and stop and wait. Now, that is for the noiseless channel. Now, in reality, no channel is noiseless. This was just as a starter, it just assumed that there is a noiseless channel, and if there is a noiseless channel, this is how a flow control mechanism can be used. But in reality, we have a noisy channel, and the first protocol, rudimentary protocol that was used, was stop and wait ARQ, or automatic repeat request. That was when it received a packet from the network layer, it will start sending the packet to the destination machine, and it will wait. Now the destination machine will be sending an acknowledgement that okay, I've got your message, and then it will wait for another messages from the, or it will send the other message if it has to send one. Now, till it receives the acknowledgement, it will hold the message it has sent in a buffer, and if for some reason the destination machine is unable to get that message, it will resend the message. Now that is actually decided using a timer, which is set that if the timer goes off, it knows that for some reason the message hasn't been sent to the sender, and it resends the message. Next we have go back in ARQ. Now the main problem with stop and wait was inefficient utilization of bandwidth. So in order to address that problem came go back in ARQ, where instead of sending one message at a time, it will be sending more than one message. So say 4, 5, 6, 7 messages at just consecutively, and wait for acknowledgements. So once an acknowledgement comes, now this acknowledgement is to come message by message. So if it say if it is sent if it is sent like say 4 messages, 1 2 3 4, it has got the acknowledgement for message number 1. So it will delete this message, the frame number 1, from its buffer, and again start sending other messages. Now for some reason it finds that the timer it had set for message number 2 or the frame number 2 has expired. So it will know that there is a problem in the network, so it will resend just not 2 but 2, 3, 4. But the problem with this protocol is, and in fact that is why it is known as go back in. Anyways, but the problem with this protocol is maybe the sender has received frame number 4 and 3. Maybe there was a problem with frame number 2, it didn't reach the receiver. So in that case it will be, it will be extra burden on the network traffic to actually send 3 and 4 again. So to deal with that problem came selective repeat ARQ. Now selective repeat ARQ says that now the receiver will also need to maintain a buffer. So when it receives the buffer, when it receives a message, it starts putting that in a buffer. So we assume that it has got messages 1, 3 and 4, and it has not got this message 2. So it will send acknowledgement for 3 and 4, and now the sender knows that for some reason 2 hasn't reached the destination, so it will send only frame number 2. So that goes about the flow control mechanism. Now in case of error, there can be two kinds of error. It can be a single bit error where say a 1 has been changed to 0 or a 0 has been changed to 1. And there can be burst error, that is more than 1 bits have been inverted. So now to deal with that problem, we use some bits known as redundancy bits. Now redundancy bits carry some information about the data that has been sent. So we have the parity bits. If you, some of you have actually read about those, if you have actually gone through the data link layer, you must have gone through those parity bits. Parity bits are in fact also used in computer architecture, right? So that is done using linear block coding, convolution coding, CRC and checksum. Now convolution coding is actually not in your syllabus, so you actually don't learn convolution coding. And well, if you are interested, like there is a linear block coding, so do we have a non-linear block coding too? Actually non-linear block coding is very difficult to implement, and it is also theoretically not so sound. It's difficult to actually implement that, so we don't use non-linear block coding. But yes, there is non-linear coding also. And then we have this checksum. As I said, I will be saying a word or two about checksum because checksum is very important in internet communication for your error control mechanism. It is like, say you have sent some bits, so you will take the summation of the message, the summation, say your message is like 2, 4, 6, 8, all in, of course these are actually depicted in bytes. So you take a summation of these. This will be like 4 plus 6, 10 plus 12 plus 20. And now you add minus 20 as your checksum block. Now when your receiver receives the message, so it will add these and your checksum together, and if it computes to 0, it knows that yes, it has received the correct message. But if it has seen that no, this hasn't been 0, it is going to actually ask for a retransmission. That is, it has got the wrong message, or some bits have been mangled, there might be some single bit or uh, burst error, so it will ask for a retransmission. Now the proportion or the ratio of redundancy bit to your data bit will determine if the error control will be of a forward error correction or a retransmission or error detection. Now there are some errors that is corrected by the receiver. The receiver knows that exactly here the error has occurred, so it just corrects those error and doesn't ask for a retransmission. So these are forward error correction mechanism. And in case of retransmission, like I said before, it detects that no, there is a problem, but it doesn't know where the problem actually lies. So in that case, it will be asking for a retransmission. And now there are two types of framing that is used in data link layer. One is a fixed kind of a framing, but the more important or the more used or the more what shall I say, this is the framing that is mostly used in data link layer, which is the variable sized framing. But the problem in variable sized framing is the receiver must know where the frame starts and ends. So in order to mark the end of a frame, it can use a character like the escape character, or it can use a bit oriented thing where you use a special byte. Like you start with 1, there are 6 zeros, 1 2 3 4 5 and 6 zeros, and it ends with a 1. But there is a problem with both of these. Like if this kind of a data, or if this kind of the flag exists in the data, so your receiver will assume that that is the end of a frame. So there has to be some special bits which would indicate that this is a part of the data and not a flag. And so also in this character oriented thing. And the communication protocols that are used in this layer is the HDLC protocol, which is for both point to point protocol and the multi point protocol. And we have protocols like point to point protocol again. And there are certain other protocols that are used while we are trying to implement the point to point protocol, that is the link control protocol, and some authentication protocols like challenge handshaking authentication protocol and password authentication protocol. These are used along with the point to point protocol. A part of this point to point protocol, you might see. Now the data link layer is going to hand over its message to the physical layer, or the lowest layer of both the TCP IP and the OSI model. Now we have two kinds of media for actual transmission of frame or a data, and one is a guided media, or you might say a wired media. And that wired media can be a cable type, which is twisted pair cable or the coaxial cable, and these receive electric kind of signal. And then we have a fiber optic kind of wired media, which will accept light signal. And then we have a wireless media, which is the free space, or is also known as the unguided media, and that uses, or the signal that passes through this wireless media is electromagnetic signal. So now we were dealing with data. Now that data needs to be changed to signal in this layer. and we also need to use bit encoding. Like, now when we are generating a signal, we need to find a way so that the receiver knows that which, like, which voltage stands for which bit. Like, a 5 volt might stand for 1 bit or 0 bit, so that is determined by the kind of bit encoding that is used. Then the bit duration, like for how long one bit, or the signal, for how long one bit is going to show up in a signal. And then synchronization, again it's kind of a flow control. And then there are different transmission modes in the physical layer. There is a simplex mode where just it's a one sided communication, duplex mode which is both sided communication, and there is a half duplex mode. This is also two sided communication, but at a time only one side can communicate. Now let's look into the different things that goes on in the physical layer. So first is the transmission. Now the transmission in physical layer can be parallel, and it can also be serial. In case of serial transmission, we have a synchronous transmission, which is a timed transmission. The sender and the receiver knows. So for this period of time, we will be exchanging some data or signal. Then we have an asynchronous transmission, which is not actually timed. So there some means needs to be taken for the receiver to understand that okay, a transmission is coming from that end. And then we have an isochronous transmission, which is used in case of video transmission and so on. And then we need to convert the data into signal. Now the signal can be two types: the analog signal and the digital signal. So analog signal is like a continuous signal, you might say, like the sine curve. And digital signal, it contains only discrete values, and the digital signal looks like this, somewhat like this. Now, in order for a digital signal to actually pass through a physical media or a communication channel, that kind of communication is a baseband communication. Now, the baseband communication requires that your channel will have a variety of bandwidth. It will start from zero bandwidth and it will go up to infinity in order to actually pass the signal with its proper encoding. And so the receiver gets to understand that okay, this was the exact signal that was sent to me. But the problem with this kind of baseband communication is, first of all, if you are first of all, bandwidth to infinity is very rare. All you might say that you can opt for a bandwidth which is a very high bandwidth. There will be some signal loss, but the receiver will still be able to understand what is going on, or what was the intended data that sender was trying to send me. But this if the bandwidth needs to start from zero in order for the communication, in order for the signal to pass, that means that communication media cannot be shared. So that is one of the major flaw and something we cannot afford. So what we do is we use a modulator, and that transfers the digital signal to analog signal, and now a broadband kind of communication happens where the signal just passes through the system. Now, in order to convert a digital data to digital signal, we use line coding mechanism. It will be unipolar, polar, bipolar, multi-transition and multi-level. I am not going into detail how this line coding happens, because this actually needs a whole lecture to be dedicated to only line coding. Then we have digital data to analog signal conversion, and that is used using shift keying, that is frequency shift keying, amplitude shift keying, phase shift keying, and quadrature amplitude modulation. Next, we have the conversion from analog data to digital signal. So that is done using conversion, that is delta modulation and pulse code modulation. Next, for bandwidth utilization in wired medium, we use frequency division multiplexing, time division multiplexing or statistical time division multiplexing, and wave division multiplexing. And if it is a wireless media, the same bandwidth utilization is known as spread spectrum. We have frequency hopping spread spectrum and direct sequence spread spectrum. Now, these I'm not going to explain it to you because it will be very futile to try and explain in just few words these techniques. So, of course, I will be dealing with that separately. And finally, when we send the data, we send from one node to another node. So, that interlinked nodes are also known as switch. And we have circuit switching where we make a logical connection from one node to another and we send the data. So this is kind of a dedicated connection, and we generally don't use circuit switching. This is more suited for your telephone systems. Then we had message switching where we don't actually have to have a dedicated path. We will just be sending the message to the next node that we are connected to, and then that is that node's responsibility to forward the message. But the problem with message switching was message switching did not mandate that this should be the size of the message. So if your message is too long, that switch needed to have enough buffer to actually store the message. So the same message switching, now when we mention the message size, becomes a packet switching. So we just say that no, the message size should be so and so, maybe just one byte or something, and when that fixed size message is used, it becomes a packet switching. And now packet switching can have two types of switching technique. One is the virtual circuit, another is a datagram. So virtual circuit is actually used in HDLC protocol of your data link layer, where you have a kind of dedicated logical connection, and this is the datagram, which is actually universally used in your internet protocol, where you just send the data and forget about it. There is no connection set up or anything like that. And the main the main advantage of this datagram packet switching is you don't have to follow the same route always. So if there is a congestion, maybe you were taking one route, and if there is a congestion along that route, of course you will be sending the data along the other route which is less congested. So that gives some dynamicity to forwarding these packets. So for that, datagram is a highly datagram is very much used in your data packet forwarding. So now that was all about the lecture, and this is, I have tried to give you an overview of the entire networking, the layers and the important protocols. What I left out is the topology, the network topology. We have the bus topology, ring topology, then we have the mesh topology, the star topology. I have left out those parts because I think the video is getting too long. So if it has helped you in any way, please do give me a thumbs up, and do consider subscribing to my channel. So that's all for today. Thank you.